Thank you, everyone. I'm a local speaker, which also is translated to I'm probably the cheapest speaker you've had, right? Because there's no flight and there's no hotel, but I will pass you my bill for the petrol. So yeah, anyway, thank you for attending this talk on asynchronous programming in Kotlin. I will, there's some code, but through the slides I'll use this and then we'll switch over to the other mic. So how many of you here have heard of Kotlin? Oh, that's nice. How many of you have heard of Kotlin before Google I/O? You see, just half. Okay, great. It's like I always say, I should have spent the last 6 years of my life just staying at home and waiting for Google I/O to talk about Kotlin than me. But anyway, how many of you use Kotlin? Right. Now the most important question, how many of you are doing Kotlin that is not related to Android? Okay, there's a growing number of us, which is great. Someone asked me, is Kotlin just about Android? I was, no, it's not. So anyway, this is asynchronous programming, and if you're old enough as me, you probably remember that. Which was a lot of fun. It was, used to. But there was a game on Windows. I don't know if you remember. It was called Solitaire, and when you win it, it would make these like things. I would never win, so I would just make my apps hang, and then do this on my own. So asynchronous programming is hard. You probably all know it's hard. And there's different approaches through time that we've tried to use for asynchronous programming. And I'm going to give you a brief history of these, and then show you how we approach this using Kotlin. So one of them that you all probably know is threading, right? Where I have basically some code and I have a bunch of functions, and this is Kotlin if you're not familiar with it. Fun over there means function. That's the name of the parameter, the type, the body, and that's it. And that's how you declare a function in Kotlin. So here I have a function in Kotlin that's token, prepare post, that returns a token, and then I submit post. Now if I'm doing this on the main thread and one of these functions is going to take a long time to run, what I don't want to do is block that main thread. So the thing that I do is I go ahead and create a new thread and launch that in another request. And that's very simple. Like launching a thread is actually really, really simple. The problem with threading is that, first of all, it becomes complex because you have state mutations, right? They say stay away from state, and they say stay away from state even more if you're doing threads. Then you have to combine the threads that you're using with your UI thread. Then you have to do debugging of threads, which how many of you actually enjoy debugging threads? Yeah, okay. Anyone that puts up their hand, they probably also like JavaScript as well. Then you have the unviability of some scenarios. Like, there are certain scenarios, there are certain platforms that do not allow you to have threaded systems. So you have to fall back onto some other model. And it is limited. It is limited because of the underlying operating system. In fact, normally when I do this launch when I'm doing this talk, I show a demo of how to launch threads. And when you launch about 100,000 threads on Mac OS, it dies at some point. Like very, very soon it's going to die and it's going to say unable to launch native threads. Recently I upgraded to Mac OS Sierra and I launched this live on a demo with 700 people in front of me, and it wasn't dying. And I'm like, oh, maybe I'm running the wrong app, and I launched it again and it wasn't dying, and it just wasn't dying. And what has happened in Mac OS High Sierra, it's actually much slower to create threads. And the way my code was, it was giving enough delay for the operating system to actually continue to create threads, but it would eventually die. But meaning that the underlying system is going to have resource limitations. And of course you have the context switches, which is expensive when you're doing threading. So now there's another model, right? So let's say that threading isn't the best model. Let's look at the other models that there are. There's another model called callbacks, whereby I have a function, and again, if you're not familiar with Kotlin, this over here is essentially a lambda. All of this code over here, that's a lambda. So in Kotlin, the last parameter to a function, if it is another function, you don't have to put it inside brackets. You can just put it outside of the brackets. This function only has a single parameter, which is a lambda, so the lambda is represented as so. As you can see, this curly braces, the parameter of the lambda, etc. So in this example, what I'm doing is I'm using a callback model, whereby I'm invoking some action and I'm saying, when that action completes, then call this function. Now this is pretty nice, right? Because I have my function that I'm calling that's called prepare post async, and then it passes in a token. It takes a lambda that takes a token and returns nothing, and then I call it using the lambda that I'm passing in. This is good, but again, this also has a certain level of issues. First of all, it's complex in terms of error handling. How many of you do Node.js? JavaScript? No. Okay. So in JavaScript, they've got this thing called callbacks. And normally, when you write functions in JavaScript, the first parameter is the error, represented as an E. Many people choose to ignore it, or they think it's an event, and they're like, I'm not interested in events, so I'll just ignore it. So on top of having complex error handling, you also have environments where people just don't care about error handling. Then you lead into what's called the callback hell, which is also often referred to as the tilted Christmas tree, right? Because if you look at it from the sideways, turn it around, that looks essentially like a Christmas tree. And that is because you have callback after callback after callback. All of these nested callbacks essentially become unreadable. Now there's other solutions as well. Some of them have even come to JavaScript. So for example, in Java you have futures. In JavaScript you have promises. Why didn't they call them futures? I don't know. There's different versions of promises in JavaScript. There's those that don't like the word promises and call it commitments. And I'm not joking, that's not even funny. So, you know, there I'm saying, okay, I'm going to return some value, and then on that value, I'm going to change some operation. So here I can say, well, prepare a post, then I'm going to compose that with something else, and then then accept, and so on and so forth. Now you're introducing a bunch of things. You're introducing these new operands. You're introducing the new type over here, which is promise, which now says I'm returning a promise of a type token, and I have to introspect that value to get that value out. And then comes all of these operators that you have to learn. Because first of all, error handling also isn't that straightforward with promises and futures, but then you start to enter this paradigm of now I've got to combine these promises, and I have to learn new operators of how to combine these different aspects. There's a similar approach to this also, which is called reactive extensions. Anyone heard of reactive extensions? Right? So that came from C#. It was called reactive extensions. Nobody took notice of it until Netflix ported it to Java. They called it RX Java, and the whole world blew up around reactive extensions. So reactive extensions, now there's RX Java, there's RX Scala, there's RX Kotlin, there's RxJS, there's RX. There is no RX C# because it's reactive extensions. But anyway, there you go to a model where you have what they called observables, and then things that subscribe to those observables. So it's kind of like a twist on the observer pattern. And essentially you have this observable interface where things can subscribe to, and then the observer will act based on the next value coming in, on error, on completed, etc. Now, when you start to play with RX Java, the first thing they tell you is everything is a stream and it's observable. That is essentially the way they introduce you to RX Java, which is kind of similar to that comics, like, did you just tell me to go? And yes. That's what they're saying to you, right? Because you're moving from a shift, from a way of thinking, to now treating everything as an observable, which is essentially an infinite stream of values. And then what you're doing, you're subscribing to these values. And then on these subscriptions that you do, you perform different actions. But you shift away from your normal way of thinking. You shift away from that top-down approach of programming and moving to a different programming model. So again, it comes back to new ways of combining things, new way of learning things, having different operators, doing all of these things. So those are many ways in which you can do asynchronous programming. I'm not saying any of them are bad. I think, in fact, RX Java is a very elegant, nice way to do asynchronous programming. However, each of them come with their benefits and their downsides. So what did we do in Kotlin? Kotlin we introduced, well, we didn't introduce. I mean, coroutines is a concept that has been around since the 1970s, if not more. And we adopted the aspect of Kotlin, of coroutines. So coroutines is essentially the idea behind suspendable computations, and we'll get into it. But we did it from a way in which, very similar to the language itself, in that one thing that we've tried to do very hard in Kotlin is not commit to forcing you to do things in a specific way. So if you look at the language, a lot of the things in the language aren't actually keywords, but they're functions of a standard library or external libraries. And that is how we've introduced asynchronous programming in Kotlin. There is very little in the language itself, and everything else basically is provided by libraries, as we'll see. But the idea behind coroutines is essentially for you to do asynchronous programming the exact same way that you would do synchronous programming. So you don't have this paradigm shift, you don't have to think about things differently, you just continue to do things more or less in the same way. In essence, same way of thinking from asynchronous to synchronous. Same way of doing things. If I want to handle exceptions, I put my try-catch, exactly the same way. If I want to do a loop, I do a loop. Everything exactly the same. Same constructs. I don't have to learn absolutely new things. Okay, with the exception of 3 or 4 library calls, I don't really need to learn new things in order to do any kind of asynchronous programming. And what is the idea of coroutines? It's essentially the concept of suspendable computation, which essentially means that I will have a function that at some point is going to suspend, and you can do something, and then at some point that function is going to resume. That is essentially what it boils down to. A function that can be suspended and then later resumed. The difference is, one of the main differences is that this moves towards what we call cooperative multitasking as opposed to non-preemptive multitasking. Sorry, as opposed to preemptive multitasking. So whereas with preemptive, with threads, you have the thread, and the thread is basically switching context in and out. When you're programming with coroutines, you're conscious about that you're doing a cooperative multitasking, and you're responsible for handling certain situations in terms of suspending your function, resuming it, making sure that your function can be suspended, making sure that your function can be cancelled, and so on and so forth. But it's about cooperation. It is not for CPU-intensive operations. Coroutines work great for non-CPU bound operations, right? Things that actually make sense to be suspended at a point in time. It is essentially, under the covers, a state machine with CPS, which is continuation passing style, which is a very eloquent way of saying it's callbacks. So coroutines are essentially callbacks that are handled for you under the covers using the state machine and the compiler. And it's handled by the compiler, meaning that it is not bound to the actual platform that you're working on. You could think about coroutines as lightweight threads. They're not actually so, and to say lightweight threads, if I launch 1 million coroutines, well, if I launch 1 million threads, I'll wait for 7 years on macOS for it to finish. If I launch it on Windows, it'll probably give me a native thread exception. If I launch but it'll try and launch 1 million threads. If I launch 1 million coroutines, it's not going to launch 1 million coroutines. It might launch 5. It might launch 20, right? What launches and how it's launched is kind of dependent on the underlying compiler and some parameters that you can define. How do they look? This is a coroutine, okay? So the first thing you'll notice is that this function over here is my post item, and I have my token prepare post and I have my submit post. The only thing different from the original one that I showed you is that launch at the top over here. So you see launch there is just a thing that we've introduced, which is a library call which allows you to launch coroutines. And what is launching a coroutine? It means that you can actually call a suspendable function. What is a suspendable function? It's the thing at the bottom over here. Now, if you look at the signature of this function, it is exactly the same as if I were to just declare a function in Kotlin. The return type is token, which is the type I want. It is not a promise of a token, and it's not a future of a token. It is just a token. It is not a task of a token. The only difference is that keyword in front of it, which is called suspend. And that is essentially the only thing that the language has added. A suspend keyword and an implicit argument which is called continuation, which you never have to ever touch. Okay? So how does this work? Well, first of all, as I said, it's a natural signature. The only thing that's different is a suspend function. And what I do is I explicitly launch that coroutine. So I go, if I'm running this on the main thread, this is going to go prepare the post, and if the post is a blocking operation, it is not going to block the main thread. It is going to go and do it in some thread, and when that thread resumes, then when the process resumes, when the function resumes, it will come back and it will do the submit post. So when I'm writing the code, it is as if I'm writing synchronous code without having to worry that it's actually going to block my main thread. And that is done inside this launch, which is the actual coroutine. Okay? When you're running this in an IDE, such as, well, I don't know any IDEs, but maybe you use something called, I don't know, IntelliJ IDEA or something like that. You see these little symbols over there on the side, which is indicating that this is a coroutine. Okay, this is a suspendable function. So, how do they actually work? Under the covers, what this is going to be translated, first and foremost, please, Kotlin does not translate to Java. Kotlin compiles to bytecode on the JVM. On native, it goes through LLVM. On JavaScript, it goes to JavaScript. But for the sake of argument that you understand what's going on here, I'm just using Java. So this suspend function submit post, what this is going to do is translate into an object with a method called submit post and the token, and then this continuation post, which is the actual callback. So under the covers, what the coroutine does is create a callback for you. Except you don't have to pass that callback in, you don't have to worry about the nested calls, you don't have to worry about any of that. That is done for you by the compiler. And then that continuation is very similar to the observable pattern that we saw with Rx. I have a context, which basically gives me some information about the coroutine, which we'll see why that's useful. I have a resume, which tells me when the function is resumed. And I have a resume with exception, which tells me when the function has resumed with an exception, as the name indicates. Under the covers, what that does is have the compiler essentially create a state machine. Now, if you're familiar with C#, anyone does C#? Async await, very similar, except in C#, async await are keywords. In Kotlin, they are not. They're just library calls. Okay? So under the covers, Kotlin on the JVM, or on the compiler, it is implementing this as state machines, and then if I'm running this on JVM, it's using threads. If I'm running it on JavaScript, it's going to use event loops. If I'm running it on native, it will use worker, threads, or whatever. Okay? So let's see some code. Now I'm here. Can you still hear me? No? How many people here are actually from Malaga? Okay. So you're normally loud. I mean, we're normally loud people, and you're so quiet today. I don't know what happened. It's okay. I always say that I am allowed to insult my own hometown. Right. Okay. So here's some code, and I hope that you see this okay at the very back. If not, bigger, even bigger than what I already made. Is that good? No? I mean, what they could have done is made this room a little bit longer, because that would have been really nice. Is that better? It's not even changing, is it? Is that better? Is that better? Okay, now I've got to zoom. Okay, so what I have here is, first of all, ignore that thing called experimental. It was probably the worst decision anyone ever made, because now everyone thinks that Kotlin coroutines are experimental and we shouldn't use them. No, they're not. We're using them in production. In fact, we have a framework written on coroutines, which is called Cater, which is like a web framework. They're not experimental in the terms that you can ship production code. It's absolutely fine. This is what happens when developers don't talk to marketing. So what this is your main function in Kotlin, and I have a print line starting here, and then what I'm doing is I'm launching this suspendable process. Okay? Now this suspendable process, essentially what it is a function that is going to delay 2 seconds and launch, and then print in process. Okay? Now, first let me show you the equivalent with a long-running process. Okay? So, a normal threaded process, so to speak. Here I have a function print line, starting here, long-running process ending here. So this is something completely normal that you've seen, right? A thread sleep of 5,000. If I run this, what is the output going to be? Anybody? Don't say it's going to print some characters in the console, because that much we can get. Okay, it's gonna print starting here, and then what is it gonna do? Wait 5 seconds, and then it's going to print ending here, right? So see, it's starting here, wait 5 seconds, ending here, and in process, right? Why? Because I'm running this on the main thread. When I launch the long-running process, it will essentially going to do what? It's going to block that for the 5 seconds and then run the other thing. So let's see the equivalent of what we just saw with the suspendable computation. Now, in this case, everything is exactly the same. The only difference is 2 things. One of them is I've added the suspend in front of my function. So I'm saying that this is a suspendable function. The second thing is I've added this launch, which is essentially saying that I can launch this coroutine. Now, why do I need to add this launch? Because if I come here and I write suspendable function, suspendable process, right, it's going to give me an error and saying suspend function process can only be called from a coroutine or another suspend function. So, because otherwise the code, it wouldn't know how to handle that coroutine. So that's why I have this launcher that allows me to launch these coroutines. The other difference is that I've got this delay here. What is delay? It is exactly the same as thread sleep, except it's not thread sleep, right? To all practical purposes, delay is essentially a way, it's a sleep that allows me to cancel a coroutine on it, and we'll see why that's important. So if I run this, you see that what's happened is that it says starting here, ending here, and in process is never printed out. Now, why isn't in process printed out? Exactly, because by the time the delay of 2 seconds happens, the main thread has ended, right? So it's not able to actually wait for that to end. Now, something you should never do in life, well, you can, but while true, put an empty block of code and essentially wait for this to run so that I could show you the output. Now, I would love to do that, but probably it won't work because we recently introduced a bug in Kotlin, which, yes, we won't talk about that. Okay? So, the good thing is it's a known bug and it's going to get fixed. But the point is that the problem that you don't see it is because this is actually launching this off of the main thread. So now I'm not going to be able to see this coroutine. Okay? So how can I actually see this coroutine? Now what I can do is obviously I can put like a delay over here, right? I can say a delay of 4,000 or whatever. Or here I could put a thread sleep, and then if I run this, then you will be able to see it, right? So let's try and run this and see if that works. Right? So you see that now the thread is sleeping for 4 seconds and then it shows the in process. Okay? It comes back. Now again, this is not what you normally do, because what you want to do is very similar to thread sometimes, is that you want to launch a coroutine and then at some point you might want that coroutine to join another coroutine. And for that, there is this function in Kotlin which is called run blocking. Now run blocking is one of those things that you only use with coroutines when you're doing 1, demos, 2, unit tests, right? And what run blocking does over here is, you still see at the back? What run blocking does is essentially another function. So the syntax here, if you're not familiar with Kotlin, I can essentially write any function as a single expression in Kotlin, right? So I can run fun x int equals x plus 1, right? That's essentially what I'm doing. So I don't have to put a return x plus 1. I can just write it as a single expression function. So what I'm doing is writing this as a single expression function. And what is run blocking? Run blocking is actually a coroutine launcher. So what it does, it allows me to launch coroutines, just like launch does, right? So in this case, what I'm doing is I'm launching a coroutine, and then inside this coroutine, I am now also launching my coroutine that is going to call this suspendable process, and then I'm using delay. I can now use delay here because delay is part of a coroutine. If I were to put delay outside of run blocking, it wouldn't work, because delay, again, is a suspendable function that only works inside the coroutine. So this is another way, the correct way, so to speak, for you to see the exact same behavior, right? Because this time it's using delay 4,000 to actually see the result. Now, again, you don't really time how much you're going to write, how much it's going to take and try and time it. What you can do is something similar to how you have with thread joins, right? So here I have job join. Now here I've introduced two things. One of them, job join, and the other thing is a job. What is a job? Well, that's the result of launch. So when I launch a coroutine, I'm getting back an actual object, and that object is my coroutine, right? And I can start to work with that coroutine. So job join, the join is similar to thread join in that what it does is it allows me to join another coroutine, right? So in this case, I have run blocking, and I'm launching this coroutine, and I'm saying wait to join the run blocking coroutine, right? Have the job join the main one and then terminate. So in this case, I don't need to put a delay. I can just run this. As soon as in process is done, print it, it will then terminate the process, right? And this allows me to then have one coroutine, and then inside of that coroutine, in all practical effect, I actually have a child coroutine. I have a parent coroutine, and inside of that, I have a child. Okay, so what can I do? Well, first of all, before continuing on with the job, this is the example that I wanted to show you, right? So here is 100,000 threads. So essentially what I'm doing, this is normal thread. There's nothing coroutine-y about this. Coroutine-y, I just made up a word. And what I'm doing is I'm launching these threads, okay? Now, normally if I were to run this in an application, it will probably die on me because it will say, not enough threads, not enough native threads. Here it will essentially go on forever. I mean, we could sit here for a few hours and it will just, well, not a few hours, well, 100,000, and it will just go on, right? Now, with the coroutine version, I'm doing exactly the same thing, okay? The only difference is that here I'm launching coroutines, I'm printing, and I'm delaying each one the same way. And if we were to run this version, you can see that that will essentially run, finish, and it's taking longer because in this case I'm doing 1 million, in fact, not 100,000. Let me put that down for you for 100,000. I'm like, this is taking way too long. So before we run it with 100,000, this time I'm going to run it with 100,000 coroutines, and it should complete. And this is why you shouldn't actually do demos. So, I'm going to seriously kill Apple. I don't know why yeah. Anyway, that is very weird because this should be running. Trust me, try it at home. You know how they say don't try this at home? Try it at home, it works. Okay, so this essentially is going to finish in just over a second. Now, let's go back to some other things. Working with those jobs, right? So here I have that job, and I said that one of the things different from thread sleep to delay is that delay allows you to interact with the coroutine in a cooperative way, okay? So what I'm doing here is I'm delaying for 4,000, and then inside my long-running process, I'm delaying for 10,000, but then immediately after that 4,000 delay, what I'm doing is I'm going to cancel the job. So this effectively allows me to now run this coroutine and cancel it before it actually completes, okay? Because it's doing it in a very cooperative way, right? So you can see that after 4 seconds, this is essentially going to cancel and not show the results of that. So why is that possible? Well, if you take a look at this code, right? This is how you would normally write your, well, no, you wouldn't normally write your code like this. But let's assume you were to write your code like this. I'm launching a coroutine, and then I'm doing a while true, doing some operations, and then delaying, and then essentially when I finish, I will do some other operations, okay? But I have this while true here. Now, if I run this coroutine, what will happen is that it's not going to be cancelable. Because I can't, the job that it gives me back, if someone calls job cancel on it, it won't work because of this while true loop. Because it's not doing the implementation isn't cooperative. It's not saying that if you cancel me, I will stop processing. So the correct way to do that is to use a flag which is called isActive. And what isActive does is just say, if the coroutine is active, then I will continue. If it is not, then I will stop. So what is isActive? It's essentially a Boolean that the coroutine dispatcher will set, saying, you know, if cancel is called, I will set isActive to false, and therefore this coroutine can effectively be cancelled. And where does isCancel come from? Now, when I first showed you about coroutines, I said that one of the things that the coroutine has is a context. That context is what holds this property isActive, just like it holds a bunch of other information, right? So the coroutine scope is an interface that holds all of this information that you can actually access and work with the coroutine. But it comes with other things as well. So for instance, a timeout. A lot of times what I want to do is launch a process and say, you know, if that process doesn't complete within X amount of time, then cancel it. Now, I could do that with a cancel as you saw before, or I could just use a new construct, which is called with timeout. And this with timeout, again, is not part of the language. It's essentially a function. It's a suspendable function that allows me to pass in a lambda, a block of code, and then operate on that block of code. Very much in line with the philosophy of design of Kotlin, right? Everything essentially can become a function. So here I'm doing a with timeout of 3000. I've got a delay of 5000. Again, as you can probably guess, if I run this, it is not going to complete because the timeout is going to launch beforehand. So you can see that here I get a timeout exception because the coroutine didn't have time to complete. Okay? But we continue to go with the top-down approach. And talking about top-down approach, take a look at this code, right? So here I have some code which measuring time in milliseconds is essentially nothing to do with coroutines. It's part of the Kotlin standard library. Can you guess what it does? Anybody? Because you're all falling asleep on a Friday afternoon. It measures times in milliseconds. Well done. There you go. We could have called it MTM. And then you didn't know what it's called. That's a good thing about, like, we're good at naming, right? Right? Generally, we're good at naming functions, yes? Yes? No, we're not. Don't lie. Actually, and this is not a joke. This is not a joke. This is a true story, and I really hope that they're not in the room, because I used to have a customer somewhere in the region of Andalusia, which I will not name, and they used to have a function. I used to do code reviews for them, and they had a function which was called fecha para Paco. And one day I asked them, I said, for those that don't speak Spanish, fecha para Paco means date for Paco. And I said, what is this? They're like, oh, that's Paco. We're like, I know it's Paco, but what do you mean? Oh, Paco likes his dates in that format. I'm like, but there's two Pacos in here. It's like, no, the other one's called Francisco. Francisco, of course, is the longer term for Paco. I never went back. When they started to do fecha para Paco 2, I just said, that's it. Okay. So anyway, we do name our functions properly. So here we have measure time in milliseconds. And I have a function 1 and a function 2, and then this is result 1 plus 2. Okay? Now notice a couple of things. First of all, this is a suspendable function. It's got an int, right? So I'm returning an int. I'm not returning anything weird. Okay? This is going to delay 1. This is going to delay 1. They're going to return a number, and it's going to add the result. If I run this, how long is it going to take? 1 second. Who says 1? Who says 2? You're all wrong. It's going to take slightly over 1 second. I mean, slightly over 2 seconds. Okay? 2017. And if I run this again, I'll probably give me 2018. So why is this taking 2 seconds? Because one of the premises of coroutines is write code like you used to write code. Yes? Write code as if you're writing sequential synchronous code. So if this were to suddenly take 1 second, you'll be kind of like, wait, what happened just there? It takes 2 seconds because while it's not blocking the main thread, it is still doing function 1, function 2, and then add the results. Because it is sequential, right? One after another. So that is under the premise that in Kotlin, or at least the Kotlin team, we believe that you need to be explicit around concurrency. Right? You need to actually be explicitly saying that this code is now running concurrently. So how can I do that with Kotlin and coroutines? You can't. Find a different solution. No, I'm joking. The way you do that is using async. Right? So those of you from C# probably are familiar with async await. Okay? Whereas in C#, async await are keywords of the language. Here they're not. Here they're just functions. So here I have a function async, which I can dive into, which is a function that takes a coroutine context, a block, which is a suspendable function, and I have function 1 and function 2. And I'm doing result is 1.await. And again, notice that await is going to give me back the actual result. It's not I don't have to do an introspection of task of whatever. I can just get back the result. And if I look at await, again, that is just a function. So if I run this, how long do you think this is going to take? Now this is easy because I've told you it's concurrent, right? It's not going to take 2 seconds. It's going to take how long? 1. If people are saying 1, you still got it wrong. It's slightly over 1. Okay, so you see that this takes 1 second. And this is asynchronous. This is saying, yes, I am going to execute these concurrently. Okay. Now this async also takes some other parameters. One of them is the coroutine start. And what is that coroutine start good for? Well, you can do lazy starts. So this is again exactly the same block of code. I just formatted it to confuse you a little bit. And I'm doing exactly the same thing. I'm doing await. If I to run this, how long would it take? The only difference is this parameter called lazy. So what do you think this is going to take? How long? Slightly over 2 seconds. Well done. Why is it taking slightly over 2 seconds? Because it's launching the coroutines in an asynchronous way, in a lazy way. So that means that until I don't call await, it's not going to actually be launched, right? So here I call await, then plus, and then I call await second, and then it will essentially launch the second coroutine. Okay? Now, coroutines come with a bunch of different things, and one of them is the dispatcher. So every example that I've shown you, let's go back, for example, to the first one, suspendable computation. Here, notice that I've got a launch, and again here I have also other parameters. Now, but this launch parameter is the common pool, and you might be wondering, what is this common pool? So very much like Rx, coroutines basically work with different thread pools, right? Difference being that, again, one coroutine does not equate to a single thread, but there are still thread pools. And those thread pools, we can essentially define how they're what thread pool is being used. So common pool is as you guessed, the name, just the common pool, the one that you would probably use. Unconfined means I don't care if there is any affinity of this this coroutine with any different thread. So it can go on any thread pool that I care. Because one thing that you can guarantee with a coroutine is that the thread that it starts on might not be the thread that it finishes on. The pool that it starts on, if you want it unconfined, might not be the pool that it finishes on. Then you can have, for example, your own single thread context. And this is useful for certain scenarios where, for example, I want to do certain updates. But we don't do it in this way. There's actually built-in support for this. Okay? And then the coroutine context is another dispatcher that says essentially launch it in the same context as the parent coroutine. Because remember when I said that when I do run blocking over here and I do launch, launch becomes a child. So the coroutine context corresponds to the context of the parent, which in this case is run blocking, right? So this allows me to now launch different coroutines in different dispatchers, which is very similar to, again, if you're familiar with Rx, you have the on-subscribe, the different dispatchers, and the on-publish different dispatchers. You kind of get the same behavior here, okay? So now we start to get a little bit more interesting on things that the coroutine provides you, such as, for instance, channels. So channel is a way for a coroutine from one coroutine to send some information to another coroutine, right? So I can create a channel of integers, and then I can launch my 5 coroutines in this case, and I can send information via this channel, and then from another coroutine, receive information from this channel, right? And if I were to run this, you can see essentially 1, 4, 9, 16, 25 being sent from one channel to using the channel to send from one coroutine to another coroutine. That is one way that coroutines can cooperate in terms of data. Now, this concept of channel, you can extrapolate to the idea of essentially having infinite streams, sending infinite amount of information, which is represented by what we call a pipeline pattern, right? So again, similar to RX Java, where I can just have a pipeline of information being sent from one coroutine to another coroutine, and having the option to close the channel on one end, stop receiving on the other end, and creating a continuous stream of information between multiple coroutines that can cooperate. Right? And this isn't only a one-to-one, because you can go to the next level and even have options like fan in and fan out. So you have multiple channels receiving from multiple coroutines receiving from one, multiple coroutines sending to the other way around, and so yeah. Meaning that, you know, there are multiple ways in which coroutines can collaborate. If you want to do shared state outside of these channels, how can you do it? So that's what the single threaded context that I was just mentioning provides us. I can actually have a single threaded context and use that context to cooperate in shared mutable states. If you really want to do that, you could use a threaded context and have your coroutines launch on that single context to be able to cooperate in terms of updating data. Okay? On top of this, we can also build the actor model, if you're familiar with the actor model. So now I basically have a coroutine with its state and with means to communicate with other coroutines, and I can now essentially send information back and forth and have each of these running in different places. And we'll see an example of this now, which I'll show you. How many of you do mobile development? Good. I was going to show you my typical Android Studio example. I'm not now. I'm going to show you my amazing JavaFX example. How many of you do JavaFX? Yeah, nobody. So here's an example of my JavaFX application, okay? So here's a countdown button, and I'm going to click it, and there you go. It's basically counted down my, it's stopped my countdown button. Amazing, right? Okay, that's all you're going to see there. Now I'll show you a real-world application. Well, it's nice, no? I mean, it was nice. I mean, for what it lasted. No, essentially what this is I'm going to show you the kind of something equivalent on the Android application side, which is way more realistic. So here what I have is very similar application. The difference is that I've got this counter that is continuously going to be counting, right? And I'm launching this on the UI thread, okay? And then at the same time, I'm assigning an on-click event, which what it's going to do is calculate Fibonacci. So every time I click that button, it's going to calculate Fibonacci. Now, I should have launched this last night when I went to bed so that I don't have to wait 6 hours. Oh, look how fast it is now. So if you know Fibonacci, you know that once you hit around 50, it starts to become slow. So this is actually launching those Fibonacci's, it's calculating those Fibonacci's on the main thread, well, as a top-down, as you've read, and it's also doing the counter, right? So this is counting, and every time I click, you see that it's counting Fibonacci. But notice that I keep clicking this, Fibonacci is starting to become slower, right? But it's not interrupting the main thread. I am launching this in a top-down, very imperative style code when I'm writing that, and all I'm saying is that you essentially calculate these results and shove it back to the UI thread. Not having to worry about getting the UI thread or anything like that. The coroutine takes care of it for me. Well, the library takes care of it for me. Okay? As you can see here, I launch this, I say that it's on the UI thread, so anything that happens here on the UI thread, that's simple. No problems, right? So, that's kind of like a whirlwind tour of coroutines. And I think we have 3 minutes, right? We don't have any minutes left. Okay, well then we don't have any minutes left, so I was going to ask any questions. No, that's fine. I don't have any. Okay, sorry. There you go.